So we got the volume as a function of girth. Let me just plot that again. Let me just plot that again and we'll have a look at it. So we've got this nice scatter graph here between girth and volume like that. And we want a nice way to describe the goodness of fit. We want to describe how good the fit is. And I'm going to put good in quote marks here, scare quote marks here, because I'm not really defining what good is. But basically, this is very good. This is intermediate. This is poor. And this is 0. Non-existent. So you see we've gone slightly from very good here, which is very, very close to this straight line. A little bit of a scatter. Marginal correlation. And here is non-existent because the best fit straight line is horizontal. So how do we describe that mathematically? Well, I'm not going to give the mathematical definition of it, but we use the R squared correlation for this. R squared equals 1, actually for perfect. R squared will be something like 0.7 for that one. This one would be R squared equals 0.3. And here R squared equals 0. So we have different correlation coefficients. I'm not going to define it. It's in terms of the ratio of the unexplained variance to the explained variance, but mathematically, it's a bit of a nightmare. R squared equals 1 for perfect correlation. R squared equals 0 for no correlation. And R squared is between 1 and 0. NB, this graph here also has R squared equals 1, because the actual correlation is negative, so when you square it, it gets back to positive as well. So we can use R squared to describe the closeness of the data to a line. Okay. And if it's equal to 1, you've got this system here. If it's equal to 0, you've got no correlation. And if it's intermediate, it's kind of close but no cigar. It's a somewhat confusing, but I'm going to cover it anyway, to compare R squared with the R squared is distinct from the p-value. The p-value measures strength of evidence against a null. Usually that the slope is 0. So more data gives a smaller p-value. but not necessarily a higher R squared. And I'll illustrate that numerically. So what I've done is just create some data here. X is just random data. Y is X plus that, plus normal data. So really, Y equals X plus scatter. So we know that Y equals 0 plus 1 times X. Because I've put no constant in here, they're just proportional to each other with scatter added. So if I go linear model of Y versus X, we get this. Summary. Let's just do that. So you see, we know that the true values are 0 and 1, but I'm much more interested in the R squared, which is 0.644, and the p-value, where's my p-value? 0.003. So we can reject the null, because it's true. Can you guys? If I give you more data, oops, start that again. So now I've got 10 times more data. It's the same correlation coefficient, several observations. First one is that the intercept and slope are almost exactly correct. It should be 0 and 1, and it's 0.8, which is quite close. And that should be 0, and it's just a little bit under. So that's one observation. The R squared has actually come down because we've got a lot of random scatter, and it's come down to 0.45. But the p-value has gone down to effectively 0. So we've got a situation here where R squared is staying constant, but the p-value is getting smaller because we're throwing more data at it. So the p-value measures the strength of evidence against a null, and so the p-value strongly dependent on amount of data. Whereas the R squared is a measure of the correlation between two data sets here. And we can see this if I go plot Y as a function of X, where we've got bazillions of data points now. The p-value is very, very small because you've got this overall trend here, but you can see that the actual fit is quite poor. The actual fit being measured by the R squared, which is 0.45, which is quite small. But it's a very, very significant p-value because you've got so much data. Okay, so armed with that, what does that do to our trees data set? Have I still got it? Oh, there it is. I'm not covering the difference between multiple R squared and adjusted R squared. They should be the same. You can see that they're slightly different. 0.933. So that's what 93% correlation looks like. Oh, it's gone now, but the picture, it should be still here.
If you asked to report the R squared, which one would you report?
Adjusted, I guess. Yeah, if you're asked to report the p-value, it doesn't matter, but the adjusted one's as good as any. So that's what 0.933 looks like. So it's got the deficiency that it predicts negative volume for small girths. Let's have a look at volume as a function of height. There it is. Now you'd expect the R squared to be smaller. And indeed it is. Let's have a look at that. Do that again. Instead of being 93%, it's 33%. So that says it's a much looser collection of points around the straight line. The p-value is still significant, but the R squared is quite small. Again, we've got this same feature here that the estimate is negative, the intercept is negative. So that tells me you've got negative volume, which is kind of nuts for trees that are not particularly high. So we've got that problem as well. So what we'd like to do is to account for what we want to do. We would like to include and height in our regression. So volume equals a constant plus another constant times girth plus another constant times height plus an error. That's what we'd like to do. So we can see if you had a tree and increase the girth a little bit, it would increase the volume by this much. And if you increase the height by that much, it would increase the, by a little bit, it would increase the volume by c times that change. We can do that dead easily with R. This is not a numerical sum. We're not adding the height to the girth. This is to be interpreted in the context of a formula where it means height and girth as well. So it's not a plus. Well, it is a plus, but it's not a mathematical 2 plus 2 equals 4 plus. And you'll see what happens when we do the regression. What we see now is an estimate for the interception plus 0.33 times the height plus 4.7 times the girth. And you'll see that the R squared has increased a little bit. So now V equals minus 57.99 plus 0.33 times girth, 34 I guess, plus 4.702 times height. All right. With an R squared that's increased from 93% to 94%. And you've sort of got an indication here, although it's not mathematically rock solid, that girth is a better predictor than height because the p-value is smaller. This is a p-value, always two-sided p-value, of the null that that coefficient is in fact 0. So here we've got this coefficient is 0.33 plus or minus 0.13. And this one's 4.7 plus or minus 0.26. It says it there, standard error. Somebody said yesterday, why can't I have to plot this? And it's rather difficult to plot volume against two things. Basically, if you've plotted volume against height and volume against girth, then that's enough, really, just to show you that there's no outliers or no nonlinearity. But this model also has the defect that it's still got a negative estimate. So if you've got 0 height and 0 girth, which you would reasonably expect to show you 0 volume, you get a negative volume, which is stupid. So it's still got that problem. I'll cover how to sort that out later.
I have a question. I'm trying to relate this to my fish.
Yep.
Height is length, but girth, I don't have a girth, I have a weight.
Well, you use weight instead.
Is weight instead for
Yeah.
fish?
This is just trees. No, nobody here is doing a portfolio on trees.
No.
But yeah, sure.
I was thinking
You've got a
that.
height for your fish
Yeah.
and put weight there instead.
Instead of girth. But the thing is, weight is not necessarily indicative of volume.
Isn't it?
Lead, well, think about lead, a pound of lead and a pound of feathers.
Yeah,
The volume is...
chemical weights, yeah, that's right. Chemical weights doesn't equal volume.
Well, your density is more or less 1, isn't it? You're not going to get anything 10 times denser than water, are you, in your fish? Nevertheless, you can test it. Well, just say your weight is length and girth. Just instead of my volume, you've got your weight. Instead of my girth, you've got your girth. Instead of my height, you've got your length.
That's what I'm saying. I have weight and I have length.
Oh, we'll do one against the other. I'll give you a technique for that later. We've still got the same problem here. we've still got the same problem of a negative intercept, which is a problem. And I want to leave that dangling there as a sort of tense back current. I'm going to replace the plus with a star, which is again not a multiplication. It's a different mathematical symbol. I'll show you what it does. What it does, it includes in the regression another term. We've got a plus b times the girth plus c times the height plus d times the girth times the height. I'll write that in. Which is an interaction term.
So A plus B.
It's 69.39 minus 1.29 times the height minus 5.85 times the height at girth plus 0.134 times the height times the girth. Okay? And you'll notice that the r squared has crept up to 0.97. It's bounded above by 1, so it's 97%, which is pretty damn good. However, look what you've lost. It's not clear anymore what the dependence is. If you increase the height by a little bit, it looks like you've decreased the volume because this coefficient is negative. Of course you haven't, because this one takes it up. So when you increase height, that takes it down a bit and this takes it up a little bit more. But it's not obvious. It's not obvious what's going on here. It's not obvious whether the girth even has got a positive or negative effect. If all you are is a karma whore, which is looking after your r squared, yes, it's the good model. But if you want to understand how trees grow, it's a poor model because the signs of these coefficients are negative. And also, we've got another defect of another type here, which is that if you consider a 0 height and 0 girth tree, just a seed, I guess, well, suddenly from a tree that doesn't exist because it's 0 size, you've suddenly got 69 cubic feet of wood from a tree which has got no height and no girth. And that's just as stupid in its own way as a negative finding. Somehow we want to constrain this model here to go through 0. And we can do that again by putting a 0 there. So I'll just put a 0 plus to constrain it to go through the origin in the same way that we had this morning. And again, we've got this rather peculiar sign variability. We've got the interaction between height and girth being a positive coefficient, but the marginal coefficients of height and girth separately are both negative. So it's not clear from this picture whether affecting the height on its own gives you an increased volume or a decreased volume, because that says it should be negative, this says it should be positive. Which one wins out is not clear. Look, my r squared's gone up to 0.99. So as I'm considering more and more sophisticated models, I'm getting a higher and higher value for my r squared at the expense of a more difficult to understand model, because it doesn't really make very much sense. But it's got the beautiful feature that a 0 height, 0 girth tree has got 0 volume, because I have forced it to go through the origin. Yeah? I've got rid of that term there, basically. Time's marching on. I'm going to consider one other mathematical trick. In fact, I'm going to consider 2 or 3 other mathematical tricks, and then I'll stop. I'm going to talk about logarithmic transforms. Recall. Any value greater than 0 has a logarithm. Log of x. So what I'm going to do, and you'll also recall that the log of xy equals the log of x plus the log of y, and the log of x to the n, to the power n, equals n log x. Remember that from algebra? Yeah? So what I'm going to do, instead of considering the volume, I'm going to consider the log of the volume, because it's always positive. And instead of considering the girth and the height, I'm going to consider the log of the girth and the log of the height. So my regression now looks like this. Log volume equals a constant plus another constant times the log of girth plus another constant times the log of the height, possibly plus an error, which I might ignore. So now it's log, log, and log. Now let's just have a look at this. So if I take if I take anti-logs of both sides, I've got v equals e to the a times g to the power b times h to the power c times e to the epsilon, which I'm going to ignore. Because adding the logs corresponds to multiplying the numbers, and powers correspond to multiplication. So that b log g turns into g to the power b. And this c log h turns into h to the power c, where a, b, and c are to be estimated. And hey presto, we've got rid of the problem of what happens at zero height and zero girth. Because straight away I know that 0 to the power anything is 0, so suddenly I've solved that problem. Which is rather neat. And of course, 0 height gives 0 volume because it's a multiplicative model down here. And if I've got 0 height, I've got no volume, and that makes sense. Let's see what the data looks like if we try and plot it.